Hi everyone, Mrs. Besega here, and today we're working through charging diagrams. In these, we want to show four things. We want to show that protons don't move. So we're going to start off with drawing some protons. All materials are made of protons, neutrons, and electrons. So I'm drawing some protons, and I'm drawing them in roughly the same place in the before picture and the after picture. Let's draw some electrons. Now, electrons are free to move, or at least freer to move than protons, because they're on the outside of atoms. So I'm going to draw two neutral cans. These are supposed to be aluminum cans that are conductors on top of insulating styrofoam cups. So I'm going to just leave the styrofoam cups as insulators. We'll ignore that they're there for a second. Right. And on the side, let's say we have a positively charged balloon. Now, as we write, we would write in this case that we have a positively charged balloon and two neutral cans. Now, what would happen? Let's say that in the next picture, these electrons are free to move through a conductor. Because the electrons are free to move, where would the electrons go? Would they go from can B into A, from can A into B, or would they stay put? Think about this one to yourself for a moment. The electrons that were in B are attracted to the balloon. So instead of staying in B, and this is a conductor, they're going to go through the two cans. A already had two electrons, but now it has two more. That means charge A is going to be negative, B will be positive, and the balloon will stay positive because no contact was made. The electrons moved freely through the conductors. Assume that these two cans are supposed to be touching. I drew them kind of close, but they're not quite there. Assume they're supposed to be touching, so the electrons flowed from B into A. Now, why did the electrons move? Electrons move because they were attracted to the balloon. And as a final result, A is now a negatively charged, and B is positively charged. A is negative because it gained electrons. B is positive because it lost electrons. Remember, as we do these are the four rules of charge flow. So let's confirm. Only electrons move, the protons remain stationary. Electrons will attract to protons or repel from electrons. That's what causes their motion, at least. We know that charge is conserved, so the total amount of charge should be the same. And finally, conductors allow the electrons to flow. They always try to flow away from the other electrons, while insulators keep the electrons in place. In example 1, we had two conducting cans that were touching each other, and the balloon, the positive balloon that was nearby, attracted electrons from can Y into can X. In my drawing, I drew it as charge from charge B to A, but it still works just the same. So let's confirm these four rules. In both of these pictures, only the electrons moved. That's why I drew the protons in the same place in both pictures. The electrons flowed from B into A. The charge is conserved because the total amount of charge stays the same in both pictures. In both pictures, I had 6 protons and 4 electrons, so the charge is conserved. For attract and repel, the electrons were attracted into A because they wanted to get closer to the positive balloon, so the electron motion was due to attraction. Finally, because A and B were neutral cans made of conductors, this allowed for the easy flow of electrons. They didn't flow out through the insulating cups because insulators would keep those electrons in place. So this drawing meets all 4 criteria, and the words match the drawings. Let's do another example. In this case, I have a block of wood that's an insulator with a negatively charged balloon. So all materials are made of protons, neutrons, and electrons. So I'm going to draw some nice, evenly distributed protons here. And I'm going to try and draw them the same place in the before picture as in the after picture because protons don't move. We start this problem with the balloon being negatively charged. I drew 9 electrons here There's no contact made, so I'm going to draw 9 electrons here. I had a neutrally charged piece of wood, so I'm going to draw these electrons hanging out with their proton buddies. But in the next picture, where would the electrons like to go? Would the electrons flow right towards the balloon? Would they flow left, away from the balloon? Or would they still stay still? Think about it to yourself for a moment. Yeah, they want to go away from the balloon because negatives repel negatives. So because the piece of wood is an insulator, the electrons aren't free to move all the way to the other end. In fact, I'm just going to draw them all to the left of their proton buddies. We call this state polarized. Polarized means that your material has separation of charges, and it looks slightly different for conductors versus insulators. The wood, being an insulator, shows polarization because the electrons have moved away from the balloon, but stay within the atom. Great, now let's fill in some words. In the beginning picture, the before picture, we started with a neutral piece of wood and a negative balloon. In the after picture, we have a polarized piece of wood. Notice the wood is still neutral. No contact was made, so everything stays the same charges as it was before, conservation of charge. Polarized wood, electrons repelled to the far end of their own atoms. Because wood is an insulator, the electrons didn't flow all the way to the other side. Now, what does this leave? If I look just at this end of the wood then, focus just on this little box. I have a positive end of the wood attracted to a negative balloon. Opposite charges always attract. So the wood is attracted to the balloon, and so it lifts. I call this demo greater than all the earth because this little tiny force of attraction between this positive charge and that negative charge, equal and oppositely, that little tiny attraction is actually a greater force in magnitude than the gravitational attraction from the entire Earth. The Earth weighs 6 times 10 to the 24th kilograms just about, and this little tiny amount of charge is enough to overcome that. When we say the gravity is the weakest force out of the 4 ultimate forces in the universe, that's why. Gravity is significantly weaker than this little tiny bit of charge's electricity. Again, let's recap the scenario to make sure we've got all 4 points. In this drawing, only the electrons moved. The protons all stayed in the same place. And there's the same amount of charge in the before and after picture. Again, there were 6 protons and many electrons, but the total amount of charge was conserved. For attract and repel, the electrons in the wood were repelled left because they were repelled away from the negative balloon. Finally, this gets the conductor-insulator point because it shows the wood as an insulator. Because the wood is an insulator, the electrons moved left, but they didn't fully dissociate from their proton buddies. The electrons stayed within the atom because it's an insulator, but did repel away from the nearby negative charge. So this one we got all 4 points. For the last example then, I figure let's do one with conduction. We start with evenly distributed protons. So everything is made of protons, neutrons, and electrons. We have evenly distributed protons all the way around this person, the cage. Oh, I should have drawn that in the same spot I missed. Ignore that one, not there. The protons stay still. So I'm trying to draw them all in the same place. Evenly distributed protons. Next, we have a negative Van de Graaff generator. Now, a Van de Graaff generator uses charging by friction to generate lots and lots and lots of negative charges. Ultimately, it is pulling these negative charges from the Earth, and because it's run on a motor with a belt, like over here, all right, that's the belt, those charges replenish themselves. This will stay almost exactly as negative. So I'm just drawing a large number of electrons in this metal Van de Graaff generator. We start off with a neutral cage plus person, so I'm going to draw the little electrons next to their proton buddies. Now, conduction could look like two things. Conduction could look like two conductors touching each other, where electrons are free to move through the metal. But if you had enough of a charge differential, you can actually build up enough potential difference to cause the electrons to jump through the air. Now, to be fair, you need a huge amount of potential difference. You need about 1,000,000 volts per meter. If you wanted to make a spark 1 meter long, you would need 1,000,000 volts more negative charge on one end than the positive in order to cause that jump. So let's say we have reached that. Conduction can either be moving through a conductor or sparking through the air. Electrons are going to flow through the air, so I'm going to draw that like lightning. And those electrons are going to reach this cage. Now, the cage around my person is a conductor. It's made of metal. That means when the electrons reach the surface of the cage, they're going to spread out as evenly as possible. Remember, they all want to repel each other, right? Since they all want to repel each other, they're going to spread out as far as possible. So not only are the original electrons going to move away from their atoms because this is a conductor, all right? But the newly added electrons are going to move away too. Notice that all of these electrons stay on the surface. Because they stay on the surface, nothing gets conducted into my person. I call this demonstration safe in a cage. And that's because if you are inside this metal cage, the conductor, it allows the electrons to flow away from each other, but moreover than allow them to do so, those electrons will move as far apart as possible, which always means they form a skin. They form a surface on the edge of the conductor. On the outside of conductor, the electrons are going to settle. Fun fact, if this were a spherical shape, they'd be evenly distributed on the sphere because it is a rectangular prism. They actually accumulate at the corners. So on the outside of the conductor, electrons accumulate, and that's because they repel each other. That means my person stays neutral and safe inside a cage. What this means is during a thunderstorm, the safest place to be is inside a big metal object, like a car. A car would conduct electrons all to the outside of the surface, leaving you safe in the center. In fact, as long as you don't touch the outside of the cage or the outside of the car, you are perfectly fine. And when we did this in class, we even had someone bring their cell phone in, and that was fine as well. On the last one, let us confirm that we've got all 4 points for the safe in the cage demo. This picture is the much larger one at the Boston Museum of Science, where it's 2 very large Van de Graaff generators capable of producing millions of volts of potential difference, and a person inside a very large conducting cage. So let us confirm. Only the electrons moved. The 2 places where the electrons moved is they moved through conduction when the electrons jumped through the air from the Van de Graaff generator to the cage. They spread out within the conductor, so electrons moving again, and they were free to do so because the cage itself is a conductor. So let's check for the first and last point. The total amount of charge should be conserved. In this case, because the Van de Graaff generator is running, it's okay if those charges are a little extra. Because it's running, it's continuously pulling charges from the ground and putting them on. So it actually is okay that this charge is not conserved before and after. Finally, for attract and repel, the electrons are attracted into the neutral cage because there's too many electrons on the Van de Graaff generator, so they repel each other through the air into the cage, and further repel each other through the cage to accumulate at the corners. So this got all 4 points as well. To sum up, as you're drawing flow diagrams, you're going to be drawing before and after pictures that meet these 4 criteria. The protons are stationary while the electrons move. The electrons move because of attraction or repulsion. No matter how those electrons move, the charge is conserved, so there's the same number of protons in the before and after picture, and the same number of electrons in the before and after picture. And finally, the conductors will allow easy flow of electrons, while insulators keep the electrons in place. Best of luck!